Greetings to all. In this lecture, we will see the types of probability distribution. There are two types of probability distribution, namely discrete or discontinuous probability distribution and continuous probability distribution. The discrete probability distribution of a discrete random variable capital X takes up discrete set of values x0, x1 is p of x equal to xi is equal to p of x. For I varying from summation p of xi is equal to 1, where I varies from 1 to n. Then capital X is said to follow a discrete probability distribution. Some of the popular discrete probability distributions are binomial distribution, Poisson distribution, and geometric distribution. These distributions are frequently used in statistical data analysis. It is observed that in real life too, these distributions are widely used. For example, the customer arrival pattern in a service center or a job arrival in a printer queue for printing follows the Poisson distribution. Suppose we like to study the performance of a system. In that case, generally we assume that the data are coming from standard distribution. Or if we like to simulate the performance of an engineering system, then we generate a sequence of random number from a distribution. Let us discuss what is a binomial distribution. Binomial distribution is derived from an experiment called Bernoulli trial, named after the Swiss mathematician James Bernoulli. Several other important discrete distributions are also derived from repeated Bernoulli trials. So what is a Bernoulli trial? A random experiment whose outcomes are classified as either success or failure is called as a Bernoulli trial. I repeat, a random experiment whose outcomes are classified into two categories, namely success or failure, is called as a Bernoulli trial. So let us see some of the examples of this Bernoulli trial. In tossing a coin once, the outcomes are either a head or a tail. So only two possible outcomes are possible here. In rolling a die once, the outcomes can be classified as even numbers and odd numbers. So the outcomes here are again classified into two categories. Suppose we consider the performance of a student in an examination. The results may be either pass or fail. Or in a company, in a day's production, selection of a product may be either classified as a defective product or a non-defective product. Or if we aim at hitting a target, the outcomes may be either hitting the target or missing the target. Likewise, whenever we have the cases of two options, either success or a failure, such trials are called as Bernoulli trials. Say if this Bernoulli trial is performed n number of times independently. Let P denote the probability of success and Q denote the probability of failure. Let us assume that in n independent trials, there are x number of success. Then there are n minus x number of failures. Then the probability of this event is p power x, q power n minus x. As we have said, the probability of success is p and probability of and n minus x number of failure. And say this x success can happen in any one of these ncx different ways. Then the probability of getting x success in n trials is ncx times p power x, q power n minus x. So we define a binomial distribution as let x be a discrete random variable which takes values 0, 1, 2, etc. up to n such that p of x equal to x equal to ncx p power x q power n minus x, where p plus q equal to 1. Then x is said to follow binomial distribution with the parameters n and p. So the probability mass function for a binomial random variable is p of x equal to ncx p power x q power n minus x with the condition that p plus q is equal to 1. Then x is called the binomial random variable. P is the probability of success in each trial. Q is the probability of failure in each trial. N is the number of trials. X is the number of success in n trials. So the following are the assumptions which are involved in a binomial distribution. That is, the first assumption is each and every trial has only two possible outcomes, success or failure. The next is the number of trials n is finite and independent. And the probability of success is the same for each and every trial. So it is obtained the MGF, mean and variance of a binomial distribution. So time the moment generating function, mean and variance of binomial distribution. The moment generating function mx of t is given by expectation of e to the power dx. That is given by summation x varies from 0 up to n e power dx into the probability mass function. We know the probability mass function for a binomial random variable is n cx p power x q power n minus x, which is written as n c0 e power t 0 into p power 0 q power n minus 0 plus nc1 e power t p power 1 q power n minus 1 plus nc2 e power 2t p square q power n minus 2 plus etc. The last term is ncn e power tn p power n q power n minus n. That is q power 0. We know nc0 is 1, e power 0 is 1, p power 0 is 1. So the first term reduces to q power n. The second term is nc1 e power t into p q power n minus 1 plus nc2 e power t p the whole square into q power n minus 2 plus etc. The last term ncn is 1 into e power t into p the whole power n. This is like a plus b the whole power n. So the above expression reduces to p e power t plus q the whole power n. So the moment generating function of a binomial random variable is p e power t plus q the whole power n. After obtaining the moment generating function, we can find the mean and variance of a binomial random variable x. So the mean of x, e of x is given by d by dt of the moment generating function at t equal to 0. The moment generating function generates moments. So mean of x is the first moment of x about origin. So differentiating the moment generating function once with respect to t and substitute t equal to 0. So this simplifies to d by dt of p e power t plus q the whole power n at t equal to 0. The differentiation of that function is like x power n. So the differentiation of x power n is n x power n minus 1. So the differentiation of that function p e power t plus q the whole power n is n into p e power t plus q the whole power n minus 1. And now there is the differentiation of p e power t plus q results in p e power t at t equal to 0. That is np e power t into p e power t plus q the whole power n minus 1 at t equal to 0. When we substitute t equal to 0, it reduces to np p plus q the whole power n minus 1. That is np p plus q is 1 to the power n minus 1. So we get the mean of the binomial random variable capital X is np. Or this is also called the first moment about origin, which is mu1 dashed. In order to find the variance, we need to find the second moment about the origin. So let us first find e of x square. E of x square is given by the formula d square by dt square of the moment generating function at t equal to 0. That is, differentiate the moment generating function twice with respect to t at t equal to 0. That is, d by dt of mx of t. So the first derivative has to be differentiated once again with respect to t at t equal to 0. That is equal to d by dt of the moment generating function is given by this expression. So we refer this expression in order to get the first derivative. That is np into e power t p e power t plus q power n minus 1 into e power t. So we need to differentiate this function with respect to t and put t equal to 0. Since it is the product of two functions, let us apply the product rule. So the above equation is rewritten as np into d by dt of e power t p e power t plus q the whole power n minus 1 at t equal to 0. Apply the product rule for differentiation, like differentiation of u into v. So take this function as u and this function as v and apply the differentiation. So we get np into, to start the differentiation process, u into differentiation of v is n minus 1 p e power t plus q the whole power n minus 1 minus 1, so that we get n minus 2. Now differentiation of this function is p e power t plus, now v into p e power t plus q the whole power n minus 1. Differentiation of e power t is e power t at t equal to 0. So we have applied the product rule of differentiation, that is the product of uv. So the differentiation of uv is given by u into dv by dt plus v into du by dt. We have applied the product rule of differentiation. So that is equal to np. Substitute t equal to 0. So e power 0 n minus 1 p e power 0 plus q the whole power n minus 2 into p e power 0 plus p plus q the whole power n minus 1 into e power 0. Since p plus q is equal to 1, we get np n minus 1 into 1 power n minus 2p plus 1 power n minus 1 into 1. On simplification, we have np into n minus 1 times p plus 1. That is equal to np into np minus p plus 1. We get n square p square minus np square plus np. This is the second moment about origin, that is e of x square. The variance of x is given by the formula expectation of x square minus expectation of x the whole square, or equivalently it is given by mu2 is equal to mu2 dashed minus mu1 dashed square. Upon substituting the values, we get n square p square minus np square plus np minus the mean of x is np, so np the whole square. We get n square p square minus np square plus np minus n square p square. So the first and the last terms cancel each other. So that we get np into 1 minus p, that is npq. So the variance of a binomial distribution is npq. So we have seen that the moment generating function of a binomial random variable is p e power t plus q the whole power n. Then mean of x is equal to np. Variance of x equal to npq. And the probability mass function is given by ncx p power x q power n minus x with the condition that p plus q is equal to 1. So in the next session, we will see how to solve problems using binomial random variable.